Hello students, in today's lecture we are going to solve NCERT exercise problems on oscillations. This is our disclaimer. Learning objective. After this lecture you will be able to determine whether a motion is periodic or not using some examples. Find the periodicity of a periodic function. Solve questions based on SHM and find the various parameters of SHM like frequency, time period, acceleration, velocity, position as a function of time. Alright. This is our index. There are total 18 exercise questions in this chapter, oscillations. But in today's lecture, we are going to discuss only 7 questions. Exercise 13.1. Which of the following examples represent periodic motion? So here you have to find out which one is periodic motion example. A swimmer completing one return trip from one bank of a river to the other and back. B. A freely suspended bar magnet displaced from its north-south direction and released. C. A hydrogen molecule rotating about its center of mass. And D. An arrow released from a bow. Alright. B and C options are correct. To understand periodic motion, remember the object's position must repeat after a fixed amount of time. That means every cycles takes the same amount of time, like the ticking of a clock or the swinging of a pendulum. First, let's look at example A. A swimmer completing one return trip from one bank of a river to the other and back. Swimmer's motion is not periodic. This is because the time taken by the swimmer during his back and forth journey may not be the same. This means positions of swimmer are getting repeated but time is not fixed. This means the motion does not have a fixed period, which is essential for periodic motion. This means it does not have a definite period. Therefore, this motion is not periodic. This helps us see why not all repeating motions are periodic. Timing is crucial. Alright. Now, let's focus on example B. A freely suspended bar magnet displaced from its north-south direction and released. When the magnet is moved away from its north-south alignment, the Earth's magnetic field creates a torque on it. Torque is a turning force that tries to rotate the magnet back to its original position. This is similar to how gravity pulls a pendulum back toward its lowest point. This torque attempts to return the magnet to its stable north-south alignment. Due to the restoring force, the magnet swings back and forth, oscillating about its equilibrium position. This back and forth motion is called oscillation, and it's a classic example of periodic motion because it repeats at regular intervals. So, we can say that the motion of the bar magnet is periodic. it repeats itself in a regular pattern, just like a pendulum or a mass on a spring. Now, next part, let's focus on C. A hydrogen molecule rotating about its center of mass. This means the molecule spins around an imaginary point right in the middle of its mass. When a hydrogen molecule rotates about its center of mass, it comes to the same position again and again after an equal interval of time. This is a key feature of periodic motion. The time it takes to complete one full rotation is called the period, and it's always the same for this motion. Therefore, this motion is periodic. Now, let's focus on D. An arrow released from a bow. So, the arrow only moves in forward direction. It does not return to its starting point or repeat its path. This is a different from motion like a pendulum or a rotating molecule where the motion repeats over time. Because of arrow does not come back or repeat its position, its motion is not periodic. Periodic motion requires the object to return to its original position after a fixed interval, and that's not happening here. So, we can say the motion is not periodic. 13.2. Which of the following examples represent nearly simple harmonic motion and which represent periodic but not simple harmonic motion? A. The rotation of Earth about its axis. B. Motion of an oscillating mercury column in a U-tube. C. Motion of a ball bearing inside a smooth curved ball when released from a point slightly above the lowermost point. Alright, let's see the solution. So B and C are SHMs, is a periodic but not SHMs. First, let's focus on A. The rotation of Earth about its axis. So during its rotation about its axis, Earth come to the same position again and again in equal intervals of time. This means the motion is periodic because it repeats at regular intervals. Periodic motion just means any motion that repeats itself after a certain period. So we can say that the Earth's rotation is definitely periodic motion. It has a fixed period which is 24 hours, and every point on the surface comes back to its original position after each rotation. However, this motion is not simple harmonic motion. For simple harmonic motion, the object must move back and forth about a mean position, and the restoring force should be proportional to displacement and directly towards the mean. The Earth's rotation does not have this to and fro motion. It's just spinning in one direction. This is because the Earth does not have a to and fro motion about its axis. Alright. Now, let's look at part B. Motion of an oscillating mercury column in a U-tube. The oscillating mercury column in a U-tube is actually an example of simple harmonic motion. This is because the restoring force acting on the mercury is directly proportional to its displacement from the equilibrium position and always acts to bring it back to that position. The motion repeats at regular intervals, which is a key feature of simple harmonic motion. This is the because Mercury moves to and fro on the same path about the fixed position with a certain period of time. Alright. Now let's solve the part C. Motion of a ball bearing inside a smooth curved ball when released from a point slightly above the lowermost point. So ball moves to and fro about the lowermost point of the ball when released. Also, the ball comes back to its initial position in the same period of time again and again. This regular repetition is what we call periodic motion. The time taken for one complete cycle is called the period, and it's constant for small displacements. Hence, its motion is periodic as well as simple harmonic. Figure 13.18 depicts 4xt plots for linear motion of a particle. Which of the plots represent periodic motion? What is the period of motion in case of periodic motion? So B and C options are periodic. Analyzing figure 13.1 and 13.8a. So it's a not periodic motion. 13.18a figure is not a periodic motion. Alright. Now here question arises, why? Because this represents a unidirectional motion. There is a no repetition of motion in this case. There is no repetition of motion in this case. Alright. So this is not a periodic motion. Now analyzing figure 13.8b. In this case, the motion of the particle repeats itself after 2 seconds. Alright. Hence, we can conclude that the motion shown in the figure 13.18b is indeed periodic, and its period is 2 seconds. The period is the time it takes for one complete cycle of motion. Here, that's 2 seconds, which we write as t equal to 2 seconds. Now, analyzing figure 13.8c. It is not a periodic motion. This is because the position of particles are randomly and irregular. Alright, look at figure 13.18c. Here, positions of particles are random. Alright, this is not in regular manner. This is random. So this is not a periodic motion. Now, analyzing figure 13.8d. If we look at the graph, we can see that the position repeats every 2 seconds. That means the period of this motion is 2 seconds. The period is the time it takes for one complete cycle of motion, and here it's clearly marked by the repeating pattern every 2 seconds. So, figure 13.18d represents periodic motion with a period of 2 seconds. This is a classic example of how to identify periodic motion just by looking for repeating patterns in a position time graph. Which of the following relationships between the acceleration a and the displacement x of a particle involve the simple harmonic motion? So the relationships are a equal to 0.7x, b a equal to minus 200x square, c a equal to minus 10x, d a equal to 100x cube. Alright. Let's see the solution. A motion represents simple harmonic motion if its acceleration can be represented as a equal to minus cx, where c is some positive constant. Alright, and the negative sign is crucial. It shows that acceleration always acts to restore the particle toward the equilibrium position. So among the given equations, only equation a equal to minus 10x is written in the above form with c equal to 10. Hence, only this relation represents SHM. The negative sign and the direct proportionality to x are both present, which are the key requirements for SHM. So in a equal to a equal to 0.7x, negative sign is missing. In B, a equal to minus 200 x square, power of x is 2. It should be 1 for SHM. In D, a equal to 100 x cube, power of x is 3. It should be 1 for SHM. I hope this is clear. This is a very simple question. 13.8. A spring balance has a scale that reads from 0 to 50 kg. The length of the scale is 20 cm. A body suspended from this balance when displaced and released oscillates with a period of 0.6 seconds. What is the weight of the body? Alright, so here you have to find out the weight of the body. Now, first, let's list out all the information in the problem. This helps us organize what we know before starting any calculations. So, maximum mass that the scale can read, m max is equal to 50 kg. Maximum displacement of the spring is equal to length of the scale, x max is equal to 20 centimeter. Alright, and we need to convert this to meters for consistency in SI units. So 20 centimeters is 0.2 meters. Time period when body of mass m is hanged t equal to 0.6 second. In case of spring, restoring force is given as F is equal to minus kx. The negative sign shows that the force always acts to restore the spring to its original length, where k is the spring constant and x is the elongation produced in the spring. When mass attached to spring is maximum, then elongation is maximum and force is also maximum. Alright. Therefore, maximum magnitude of force x exerted on the spring F max is equal to k x max. So in balanced state, F max is equal to k x max is equal to mg. Alright. So finding the spring constant k. Putting the value of m equal to 50 kg, x max is equal to 0.2 m and g equal to 9.8 meter per second square in k x max is equal to mg. K into 0.2 is equal to 50 into 9.8. So k equal to 5 into 98 divided by 0.2. So solving this, you will be get 2450 Newton per meter. Now, time period when another mass m is suspended from spring balance. So angular frequency, which we use to describe how quickly something oscillates, is given by the formula omega equals the square root of k divided by m. Here omega is the angular frequency, k is the spring constant and m is the mass. So omega equal to under root k by m. Putting omega equal to 2 pi divided by t in above equations gives t equal to 2 pi into under root m by k. So using this we can find mass as m equal to t divided by 2 pi whole square into k. Alright. Now m equal to t divided by 2 pi whole square into k. So putting the value t equal to 0.6 second, k equal to 2450 Newton per meter in our equation, m equal to 0.6 divided by 2 into 3.14 whole square into 2450. So it will be m equal to 0.00912 whole square into 2450. So solving this you will be get m equal to 22.36 kg. Weight of the body W equal to mg. So just put the value W equal to 22.36 into 9.8. So W equal to 219.167 Newton. Alright, this is the force with which the body pulls down on the spring balance due to gravity. Hence the weight of the body is about 219 Newton. A spring having with a spring constant 1200 Newton per meter is mounted on a horizontal table as shown in the figure 13.19. A mass of 3 kg is attached to the free end of the spring. The mass is then pulled sideways to a distance of 2.0 cm and released. Determine first frequency of oscillations, second maximum acceleration of the mass, and third maximum speed of the mass. Let's see the solution of this question. First, let's list out the information given in the problem. The spring constant k equal to 1200 Newton per meter. Mass m equal to 3 kg. Displacement a equal to 2.0 centimeter. So here we need to convert it in meters. So it will be 0.02 meter. Calculation of frequency. So frequency of oscillation nu is given by the relation nu equal to 1 by t. For spring force, time period is given by t equal to 2 pi into under root m by k. Therefore, nu equal to 1 divided by 2 pi into under root k by m. Alright. So, we have nu equal to 1 upon 2 pi into under root k by m. So putting the values of spring constant k equal to 1200 Newton per meter, m equal to 3 kg. So solving this, after putting the values, you will be get nu equal to 1 divided by 2 into 3.14 into under root 1200 divided by 3. Solving this, you will be get nu equal to 3.18 hertz. So hence the frequency of oscillations is 3.18 hertz. This tells us how quickly the mass moves back and forth. Now, calculation of maximum acceleration. So maximum acceleration A max is given by the relation A max is equal to omega square into A, where A is the amplitude and omega is the angular frequency given by omega equal to under root k by m. So therefore, A max is equal to k by m into A. Now, A max is equal to k by m into A. So putting the value of the spring constant k and mass and A, so you will be get A max is equal to 1200 divided by 3 into 0.02. So A max is equal to 8 meter per second square. All right. So the maximum acceleration is maximum acceleration of the mass is 8 meter per second square. Now calculation of maximum velocity. Maximum velocity given by the relation V max is equal to A omega. So putting omega equal to under root k by m in the above equation, V max is equal to A into under root k by m. So putting the value of spring constant k equal to 1200 Newton per meter, m equal to 3 kg and A equal to 0.02 meter. So V max is equal to 0.02 into under root 1200 divided by 3. So V max is equal to 0.02 into 1200 uh, divided by 3 under root. So V max is equal to, solving this, you will be at 0.4 meter per second. Maximum velocity is 0.4 meter per second. Figures 13.20 correspond to two circular motions, the radius of the circle, the period of revolution. The initial position and sense of revolution, that is clockwise and anti-clockwise, are indicated on each figure. Obtain the corresponding simple harmonic motion of x projection of radius vector of the revolving particle p in each case. Let's see the solution. Let's start with figure 13.20a. Here we are focusing on the details of the first circular motion. Alright, direction of revolution, the radius and initial position. These factors will determine the equation for x projection, which is what gives us SHM. It's important to connect the motion around the circle to the back and forth motion along a straight line. So in case of uniform anti-clockwise circular motion, x of t is given by x of t is equal to a cos omega t plus phi. Alright. If we change a, the amplitude of the oscillation changes. If we change omega, the oscillation becomes faster or slower. Alright. Now figure 3.20a, the time period t1 is 2 seconds. Remember, the time period is the time it takes for one complete revolution and it's measured in seconds. Amplitude is equal to radius a1 equal to 3 centimeter. At time t equal to 0, the radius vector OP makes an angle pi by 2 with the positive x-axis, but an anti-clockwise sense, that is phase angle phi equal to minus pi by 2. Sense of rotation is clockwise, so we will use negative sign with omega. Alright. Here let's write the equation for x of t using the negative sign with omega and phi equals to minus pi over 2. Here omega is the angular frequency which tells us how fast the particle goes around the circle. Phi is the phase constant which sets the starting position. Phi is the phase constant. Alright. So our equation x of t is equal to a cos minus omega t minus pi by 2. So x of t is equal to a cos omega t plus pi by 2. This setup just makes the equation easier to work with, but the physical meaning stays the same. So x of t is equal to minus a sine omega t, as we know cos theta plus pi by 2 is equal to minus sine theta. Now x of t is equal to minus a sine omega t, we have this equation. So 13.7, using equation 13.7, putting the value of omega equal to 2 pi by t. So it will be x of t is equal to minus a sine 2 pi by t into t. Alright. So it will be we have x of t is equal to minus a sine into 2 pi t divided by t So let's substitute the values given in the problem. In this problem, so the amplitude A is 3 centimeters and period is 2 seconds. Plugging these into our equation, x of t is equal to minus sine 2 pi t divided by 2. So x is equal to minus 3 sine pi t, alright, centimeter. Therefore, equation of motion of figure 13.20a for x component of radius vector of the revolving particle p will be x is equal to minus 3 sine pi t centimeter. Now, uh, analyzing for figure 13.20b, in case of uniform anticlockwise circular motion, x of t is equal to a cos omega t plus phi. So, given time period t2 equal to 4 seconds and amplitude is equal to the radius a2 equal to 2 centimeter. At a time t equal to 0, the radius vector OP makes an angle pi with the positive x-axis, that is phase angle phi equal to pi. The sense of rotation is anti-clockwise, and this direction is important because it affects the sign of the angular frequency in our equation. Now, to start, let's recall the general equation. Phi equal to general equation, that is x of t is equal to a cos omega t plus phi. So substituting phi equal to pi, we will get x of t is equal to a cos omega t plus pi. So x of t is equal to minus a cos omega t. So using equation 13.7, putting the value of omega equal to 2 pi by t, so it will be x of t is equal to minus a cos 2 pi divided by t into t. Now x of t is equal to minus a cos 2 pi by t into t. So putting the values of a equal to 2 meter, t equal to 4 seconds. So x of t is equal to minus 2 cos 2 pi divided by 4 into t. Alright. So we have x of t is equal to minus cos 2 pi divided by 4 into t. So x of t is equal to minus 2 cos pi by 2 into t meter. This makes it easier to see the relationship between time and the position. Therefore, equation of the motion for figure 13.20b for x component will be x equal to minus 2 cos pi by 2 into t meter. This connection between circular motion and system is a powerful way to visualize oscillations. Thank you for your attention. I hope this lesson was helpful.